In this video, we're going to overview a retrofit and control strategy for multi-zone units to ramp them down when zones indicate that they're not needed as much. So the objectives of this video is to really go over some basic concepts and results associated with this strategy for multi-zone units or MZUs. So we'll touch on the basics of what an MZU is, the typical issues associated with their operation. We're going to cover a really specific retrofit and control approach to these units in the field. And we're going to show the demonstration strategy and results of what's occurred already. And then we'll talk about when would you consider a retrofit like this? What would be a good candidate, and how would you go about thinking through that or looking at the data from an Army installation? And where you do have a good candidate, how do you go about thinking through some of the cost and energy savings for this retrofit? So what is a multi-zone unit? Well, many HVAC airside systems serve multiple zones, but there's really two things that distinguish a multi-zone unit. One is that you have these different decks within a packaged multi-zone unit. And here on the right, the schematics are showing a hot deck and a cold deck. So at the discharge of the supply fan, some air is sent to the hot deck side and some is sent to the cold deck side. And then the second thing that distinguishes these HVAC system types is the fact that unlike a typical variable air volume or VAV system, or even a dual duct system, where you have some zone damper infrastructure out near the zones, the zone dampers are really co-located with the packaged multi-zone unit. And they're going to mix the air coming from these decks before they get sent out to the zone. And typically these are all happening at constant speed or constant air volume. So you can adjust the temperature of the air going out to the zones, but the volume remains fixed. And that has the potential for a lot of savings as we look at how can we retrofit equipment like this that we may not be able to replace. So this is what that unit might look like in a mechanical room if we could rip off the inlet ductwork and the discharge ductwork. So air might enter here through an economizer or potentially just as outside air. And this indirect drive supply fan would then send flow through this cooling coil and some of the flow through this heating coil. So here you got the hot deck on top and the cold deck on bottom. And this array of zone dampers here is really set up where this first rectangle is going to be the first zone, and this is the cold deck side on bottom and the hot deck side on top. And the zone damper blades are oriented in such a way that when the hot deck is 100% closed, the cold deck is 100% open, and vice versa. So when you're at 50% hot deck, you're at 50% cold deck. And that is the way that the typical single actuator and set of linkages would be set up for this unit. And then you would have the discharge ductwork spider webbing out to the different places, but the only controls infrastructure you'd have in the zone would be a zone thermostat. So that's a typical hot deck, cold deck configuration. It's important to note that there are different ways of doing this. So here's a schematic and a sequencing diagram that would show how this unit is configured in a bypass with reheat configuration, where you have a cold deck, but instead of a hot deck, you have a bypass deck, and you might have a reheat coil in the zone typical to a VAV system that is allowed to heat or reheat the air for each individual zone. You also can have a 3-deck style where you can either have the cold deck operating with the neutral or bypass deck, or you can have the hot deck with that neutral bypass deck. So the important thing to note here is there's different ways to do it. You could still have a retrofit and control strategy with each of these. The simultaneous heating and cooling savings may not be as prominent because with this bypass approach, you don't necessarily have the tendency for as much energy waste. And the sequence of operation changes and the infrastructure you would need to add might be different with each of these approaches. But in general, the issues are the same. On the right, you see some pictures of the damper actuators and the damper blades themselves. And when you have that kind of actuator linkage damper setup, there's always going to be mechanical issues associated with that. What's really specific to the multi-zone units is what you see on the left here. And first and foremost is this energy saving associated with taking constant volume airflow to variable air volume airflow. And just the nature of airflow reduction to brake horsepower savings on the fans is often significant. Also, you have this by design simultaneous heating and cooling, where you're going to be heating the air and cooling the air and then mixing it together in a way that may not be necessary but is designed into these systems' operation. Also exacerbated is the constant deck temperatures that are typically associated with these systems. So not only do you have the cooling and the heating system operating together, but you may have a discharge air temperature set point for these coils that is really designed for the worst case scenario that's going to be operating all times throughout the year. And finally, included with any airside system hit list is if you have an airside economizer, chances are there's some performance issue just based on what we see in the field that could lend itself to some improvement. But the particular issue here is that now you've got a set point coordination issue where your mixed air temperature set point may be working against what your deck temperature set points are doing on the hot deck and cold deck side. So these are all considerations that if you can solve the constant volume issue, you can make headway on some of these other issues associated with multi-zone units. So a demonstration was conducted by the Army's Construction Engineering Research Laboratory, or CERL, to look at a couple Army sites and say, assuming that we can't rip out all these units across DoD due to their cost prohibitive nature of replacing them in whole with something like a VAV air handling system, is there something I can do on the controls retrofit side that could at least get them operating as efficiently as possible? And that's what was done here, looking at metrics like energy reduction, occupant and comfort implications, and the life cycle cost implications. Does it pay back? So a number of deliverables came out of that effort. So there's a full report that talks about everything from the inception of this strategy to how you contract it to how the data was collected and analyzed. But there's also tools that will help implementation of this at other Army sites. There's a design guide that will walk through how a designer would craft this controls retrofit project, as well as these design sheets for the different configuration of multi-zone units. So this is a schematic of one of the multi-zone units and an example of what would be included in that design template package that would then go to a controls contractor to implement. So this may look like a lot, but two things to note here is that one, this is the convention for DoD controls projects for symbols and annotations and point names. And two, if you have or are getting a DDC or direct digital controls set of controllers associated with your building or this system, then this is something that you should be getting anyways, and most of these points are just generally associated with the input and output of this multi-zone unit. What's really specific to this retrofit strategy are the two highlights here. So in the middle is a variable frequency driver, VFD, that would need to be introduced to take something like the supply fan and ramp it down when you don't need as much airflow. And on the left, we see an airflow monitoring array, or AFMA, or airflow monitoring station, that would be put into place to make sure that as you ramp down the airflow in the system, you're still maintaining the minimum ventilation air required by the zones. Also included in this template are point schedules for this multi-zone unit. So again, this is something we would expect with any DoD controls project, and this particular drawing is important in documenting all of the individual input, output, and network points associated with some control system for HVAC. So everything from what is the point named, what is its range in units, how do I integrate it into something like a monitoring and control front end, and once I have integrated it, how do I interface with it? Do I want a graphic? Do I want to be able to adjust it, trend it, or set some alarm for some condition that's out of whack? So this is a very important drawing in general, but here we have a couple specific points that are going to be associated with the retrofit equipment we pointed out, as well as the zone information, so that we make sure that we're pulling the zone damper command information that we can use as a proxy to tell us if the zones are happy or not, and if we can ramp the system down. So next we have this control logic diagram drawing in the template, or CLDs, and this may look like a lot, but what this is doing is telling the controls contractor how to modify or set up the sequence of operation to tell the supply fan how to modulate based on the information from the zone damper commands. And I'll start on the left and work our way right, just so we can kind of see how to read this and what this is actually doing with the sequence of operation, which is the heart of this retrofit. So let's say we had some imaginary information coming from the zones, where the zone damper commands at the discharge of this unit are all over the place, which may be typical. So what we would first do is take those hardware outputs, so what are we telling the zone damper command to do, and let's look at the highest and the lowest. So we may have to process that a bit because the zone damper command may need to be translated into what is my max heating and what is my max cooling condition for these 5 zones. Once we have that, we can say what is the condition driving what this unit should be doing. And in this case, it's cooling. And one of the dampers is an 85% of max cooling. Once we know that, we can compare it to some condition that we want to maintain. So let's say that we want to slow the system down to always maintain the most open damper at 95% open. And with a PID loop process, or proportional integral derivative, really just the PI for HVAC, then we can make sure that we can close the gap on that error based on the magnitude and duration of that error. There may be other things that we care about. So here we have another PID loop that's looking at the difference between mixed air temperature, that hardware input, and comparing that to a mixed air temperature low limit set point. Recognizing that as we slow down the fan, we may be adjusting economizer damper positions such that we need to care about the freeze condition of a cooling coil, and that may drive speeding up the fan to account for that situation. So comparing those situations, as well as a minimum speed that we may want to consider for the supply fan, we then want to take the max condition, what's really driving what this fan should be doing, and send that to the VFD either as a network variable or as a hardware output, something like a 0 to 10 volt command that would go to the VFD and ultimately drive the supply fan motor. While we're doing these smart things, we may also want to look at what the coil valves are doing. So rather than have those constant deck temperatures, we could always reset those deck temperatures based on some load such as outside air or what the zones are doing. But at the very least, what these sequences are trying to accomplish is to at least tell the controls contractor that if it seems like I don't need my hot deck or my cold deck at all based on the zone damper command information, this would be a strategy that would tell you to turn those off in those conditions. So here we have the results from the demonstration that looked at those couple different multi-zone units from those Army sites. And here there's really 2 things that we're trying to summarize. The first is how the energy use reduction was measured compared to the goal of 10%. And in all cases, that goal was far outpaced by what was actually encountered from implementing the strategy. The payback was a little more all over the board depending on the size and how much retrofit work actually had to be accomplished. We also looked at a separate effort of what would happen if you did this outside of a DDC retrofit. But really the story here is that mileage will vary based on site conditions for your utility rates, the size of your system, and the climate that you're encountering. Also, part of the demonstration was looking at impacts to occupant comfort. So that first column of data is looking at the percentage of time that there was a negative impact to zone temperature relative to set point because of this control strategy. While there were cases of impact to the deviation from set point, the actual magnitude of that was on average very, very small, and 0 occupant complaints were encountered during the demonstration period. So the result concluded from this is that there was no significant impact to occupant comfort from implementing the strategy for this demonstration. The demonstration project also tried to recognize that things like the utility rates and the savings potential and the size of the systems would all impact those payback periods. So here a matrix was made to project out what those potential payback ranges might be for your systems at your Army installations based on your specific site conditions. But how do you know if you have a system that would be a good candidate for a retrofit like this? Well, there's a few ways we can go about this, and the best way is to really use what we might be able to see about damper position to determine if we're going to hit those instances where the system could be turned down because everything is mostly satisfied in the zones. And then once we have that information, we could look at things like electrical fan savings, heating and cooling savings, and do some rough back of the envelope calculations to see if this is likely going to be something that's going to pay back. So let's start with the data. So if you have something like a DDC system that you can pull zone damper command data from, you can really see a lot on what the impacts might be. So here we have intervals of 1 minute whenever the system was on, as indicated by the supply fan status. We can determine what the zone damper effective command was. And once we have that on the left, we can go to the right, and using some data processing software like Excel, we can very quickly bin that into different groups. So what we can do is say, how many minutes did I have in this duration where I had my effective damper command from 50 to 55% open? And how does that compare with these other bins? So what that might say is that at very quick glance, if all of your operating hours were at 95 to 100% hours, then regardless of what control changes you implemented in the system, you would not be able to turn the system down in a way that would affect any savings. So here we're a little bit on the fence. We don't have all of our hours at that 95 to 100% range where at least one damper is always starved for air. But we certainly have most of the runtime at that condition. So how do we go about running some very basic energy calcs to think about, does this unit seem like a good candidate for this retrofit and control strategy? Well, one thing we can do is focus on the fan savings. So because of that cubic relationship between airflow reduction and brake horsepower savings, we can see, based on that, does it look like we're going to get enough of a bump from unloading the fan, given these runtime realities for where the damper commands are with this strategy. So for each of the bins, we've converted the minutes into hours. And if you had a 15-minute interval, you could do the same process and convert to hours in a similar way. And we may want to think about things like, what would be the likely variable air volume speed if we had a VFD on the supply fan? Well, if it's at around 50% open, we would expect we'd probably be at our minimum flow. And if we'd be at 95 to 100% open, then we'd probably need our supply fan maxed out to its design condition. And then between there, we could kind of do some type of a linear escalation of what that projected supply fan speed might be. Based on nameplate data, or even better if you had amp readings or kW measurements, you might be able to say, this is what I think my supply fan horsepower is right now running constant volume. And then on the next column, we could look at that affinity law for the cubic relationship between airflow changes and brake horsepower, and we could calculate what that cubic law would tell us the change would be. However, what we really probably want to rely on in a situation like this is the quote-unquote control curve that would recognize that because we have different dampers in this system, that as the dampers open and close, we're actually changing the system curve in a way that we're not going to be riding that system curve up and down as we modulate the VFD. So here we've just kind of taken a value in between what the cube law says we should run at and what the constant volume horsepower would be expected to be. And from that, we can translate that into a kW value, and multiplying times the run hours in that bin, we can get a kWh savings. So from here, you can sum up, and if needed, project out to what the annual savings would be for kWh with a local utility rate. Here you have your savings per hour. So this is just for fan savings. If you had a return fan, you could go through a similar exercise to account for that. And if that payback wasn't sufficient based on what you might expect, whether you do an in-house VFD addition, when you're adding that airflow monitoring array, you can look at the heating and the cooling savings using that same bin information to try to get some rough savings for what can my boiler do with less flow across that coil, or how much chiller savings might I have in my plant if I don't need to send so much flow to that chill water coil on the cold deck. And that wraps up our overview on this multi-zone unit retrofit and controls technique. So the tech transfer for this approach is ongoing. And this video is meant to be part of this approach of getting information out to Army installations to think if and how this strategy is going to be applicable to some of their systems where units may not be able to be replaced in whole with something like a VAV system. There's a lot of deliverables available that will kind of go into more detail about this strategy, but really the takeaway is just that a lot of good work has been done to think about how we can control our systems better. And for the multi-zone unit, where we are not going to be able to replace them, what retrofit and controls steps can we take that are low cost, that will not impact occupant comfort in a meaningful way? They're going to get these operating at their best in a way that is on demand, data driven, and based in the reality of how these systems operate. Thank you.